Multi-agent LLM systems are solving increasingly complex tasks, but they hit a fundamental wall when it comes to strategic prioritization. When multiple agents hold competing preferences over a shared set of options, how do you actually train them to coordinate, compete, and ultimately rank those options in a way that reflects their strategic interaction? Most current approaches rely on workflow orchestration or basic reinforcement learning. But in multi-agent RL, reward design is notoriously fragile. It's usually handcrafted, task-specific, and completely disconnected from the actual structure of how agents interact. You end up with agents that optimize for a signal that doesn't actually capture the strategic dynamics of the game they're playing. That's exactly what GARL, Game-Theoretic Reinforcement Learning, sets out to fix. Instead of hand-annotating rewards, GARL derives the reinforcement signals directly from the game-theoretic structure of the interaction itself. It formalizes multi-agent strategic prioritization as a two-stage game, an agenda allocation phase followed by an arbitration phase. And it turns the utilities from both stages into role-specific policy optimization signals. Let's break down how this actually works. In the first stage, the agenda allocation game, a set of competing agents each choose an allocation policy over a shared candidate set. Think of it as each agent distributing a fixed budget of strategic resources across the candidates. The environment then computes a shared salience distribution based on these competing allocations. The key here is interdependence. Salience isn't just revealed by one agent's preference, it's jointly shaped by the balance of power between them. Mathematically, the salience for each candidate is calculated by taking the total attention from both sides, then applying a penalty for imbalance. If one side heavily dominates, the salience drops, forcing a more balanced, strategically meaningful state. Then comes the arbitration game. A higher-level arbiter, conditioned on this induced salient state and domain-specific criteria, produces the final ranking. This creates a Stackelberg-style dependency. The allocators know their strategic emphasis will shape the arbiter's input, and the arbiter must balance that strategic emphasis with objective task criteria. To make this concrete, the authors instantiate GARL on legal issues in dispute ranking. The candidates are potential legal issues in a case. The allocating agents are the prosecution and the defense, each distributing argumentative resources. The arbiter is the judge. The judge's utility function is explicitly designed to reward legally adequate issues, while penalizing deviations from the strategic emphasis pushed by either party. So the judge isn't just picking what's legally correct, it's picking what's legally correct and strategically salient given the adversarial framing. Now here's where it gets technically interesting. How do you turn these turn-level game utilities into token-level reinforcement learning signals? GARL uses an alternating policy optimization loop. The prosecution and defense share a single allocator model, while the judge uses a separate arbiter model. Training alternates between them until a KL divergence equilibrium is reached, then switches phases. The utilities are injected as sparse turn-level rewards at the final valid token of each role's response. Then, using Reinforce++, they're converted into token-level advantages with a mask reset to handle variable sequence lengths and padded positions. This means the policy gradient updates are directly driven by the game-theoretic utilities, not by external reward models or hand-tuned heuristics. The results back this up. On the LexIssue benchmark, GARL-trained models show consistent gains across both in-domain and out-of-domain splits. The 8 billion parameter open-source allocator model actually surpasses GPT-4 in direct prompting settings. More importantly, the out-of-domain gains suggest the model isn't just memorizing case patterns, it's learning transferable prioritization strategies. When evaluated on broader legal competence via LawBench, the arbiter model shows modest but consistent improvements in structured legal understanding and application. And on GameBench, which tests strategic reasoning across multiple game environments, both the allocator and arbiter models show clear gains in active priority shaping and conditional judgment tasks. The training dynamics themselves reveal something fascinating. The loss ratio between the prosecution and defense gradually concentrates around -1, indicating a balanced adversarial coupling. They're not collapsing into a single strategy, they're actively countering each other. Meanwhile, block-level reward changes shrink towards 0, showing that case-specific optimization blocks stabilize rather than spiraling. This is empirical evidence of the system, actually converging toward an approximate game-theoretic equilibrium during training. What does this mean for the broader AI research landscape? GARL demonstrates that you don't need to handcraft reward functions for complex multi-agent coordination. If you can formalize the interaction structure as a game, you can derive principled, role-specific reinforcement signals directly from it. It shifts the focus from workflow orchestration to actual policy optimization grounded in strategic interaction. The framework is designed for prioritization tasks, but the allocation arbitration skeleton maps cleanly to policy committees, investment allocation, risk assessment, and even peer review. As multi-agent systems move from simple chat-based collaboration to high-stakes strategic decision-making, frameworks like GARL provide the mathematical and algorithmic foundation to actually train them to play the game, rather than just simulate it. If you're working with multi-agent RL, strategic reasoning, or just want to see how game theory can be operationalized for modern LLM training, I highly recommend diving into the full paper. The code and benchmarks are worth exploring, and the implications for structured agent interaction are only going to grow. Let me know in the comments how you think this approach could scale to other domains, and I'll see you in the next one.